Namaste and welcome back to Arpit course on numerical methods in civil engineering. So, module number 4, lecture number 4, the title is finite difference formulations for various equations. So, in the last 3 lectures of module number 4, we were discussing the basics of finite difference methods, how to formulate finite difference methods using backward difference, forward difference, central difference and other methods and its basics. And then also the last lecture, lecture number 3, we have seen the Laplace equation and how to formulate it and how to solve problems using the finite difference methods. So, now we will discuss the finite difference formulation for other equations, and before that we will also discuss the how to formulate the whenever to deal with the derivative boundary conditions. So, the last lecture we have seen the usage of the Dirichlet boundary condition. So, now you will see if Neumann boundary condition or derivative boundary conditions are given, then how to use the finite difference method. So, that is the first aspect we will be discussing. So, as we have already seen the previous lectures, there can be different kinds of boundary conditions like Dirichlet boundary condition, Neumann boundary conditions, then Cauchy's boundary conditions, Robin's boundary conditions, like that. So, but generally 2 types of boundary conditions are commonly used. One is the Dirichlet boundary condition and second one is the Neumann boundary condition. Here we will discuss how to use the finite difference method if derivative boundary conditions are there. So, if a boundary condition is of Neumann boundary type, that means the derivative of the function is given, then the direction derivative of the unknown field variable u x y is required or that is given. Say for example, it can be del u by del n, n is the normal derivative, so that is equal to 0 or some value. Say for example, if you consider this aquifer problem, so here this is Mahi river and then here some flux boundary comes. So, this is a Neumann boundary. So, here constant head, that is a Dirichlet boundary condition. So, here no flow boundary. So, no flow boundary means again Neumann boundary condition and here constant head. So, like that depending upon the problems we will be having Dirichlet boundary condition or Neumann boundary conditions or sometimes mixed boundary conditions. So, we will now discuss how to use the finite difference scheme for derivative boundary condition or the Neumann boundary condition. So, derivative boundary conditions are used in heat flow problems, groundwater flow problems, like that many other types of problems. So, now let us consider, say for example, consider a plate which is in which an edge is thermally insulated. So, we consider a plate like this, one edge is this edge is thermally insulated and the heat flux throughout the edge is 0. So, let us consider this x equal to x n. So, this particular this side x equal to x n is fixed and this is the right edge x equal to a of a rectangular plate of length a. So, this total length is a. So, now let j denote the element number along the shorter edge. So, here n j minus 1 then n j and this is n j plus 1. So, this is j minus 1 j plus 1 and here we consider this n minus 1 j, this is n j and this is n plus 1 j in equal distance delta x from the domain away we have taken this location. So, here R is the domain. So, x y which where 0 to x is between 0 to a and y is between 0 to b and the boundary condition we want to see is del by del x of u x and y yj is equal to u x that is equal to 0. So, that is the derivative boundary we need to consider. So, here say for example, if you the standard 5-point formula for the Laplace equation, we can write u with respect to this figure u n plus 1 j plus u n minus 1 j plus u n j minus 1 plus u n j plus 1. So, minus, so this is our point where we are formulating. So, for minus for u n j is equal to 0. So, that is the standard 5-point formula. So, we are considering delta x, this delta x is the distance from this node to this node, and we consider outside the domain another delta x, and we put it as n plus 1 j. Here as shown in the previous figure, the point n plus 1 j lies outside the region. So, here this point is outside the region, outside the rectangle. Now, since the boundary is del u by del n, that is equal to del u by del x, that is equal to u n x n y j, that is equal to 0. We can get the value of u n plus 1 j by numerical difference. So, we can take a differentiation between at this location with respect to this location and this location in the finite difference scheme. So, applying the central difference scheme, we can write u n plus 1 j minus u n minus 1 j divided by 2 times h is equal to u n x n y j, that is equal to 0. So, with respect to previous figure, so here we are taking this location with respect to this location and this location. So, you can see that u n plus 1 j minus u n minus 1 j. So, here u n minus 1 j and u n plus 1 j. So, that is what we are doing by minus divided by 2h is equal to u n x n y j is equal to 0. So, therefore, u n plus 1 j. So, if you take this equation, since the derivative is equal to 0, that value is known. So, you can write u n plus 1 j is equal to u n minus 1 j. So, therefore, the standard 5-point formula can be written as 2 u n minus 1 j plus u n j plus 1 plus u n j minus 1 minus 4 u n j is equal to 0. So, that way now we can see that we can solve this system. So, we approximated like this derivative. So, that is the way we deal the derivatives in finite difference method. So, it can be in x direction, y direction. So, in this case what we have discussed is that derivative is equal to 0, but if some flux values are given, so that also can be put it like that. So, now before further proceeding, let us consider one more example problem. So, for the given Aquifer domain, so here we consider an Aquifer domain like this. So, this is the gridding. So, find the unknown h1 to h9. So, we assume homogeneous isotropic domain and steady state condition. So, as we can see, if it is homogeneous, isotropic and steady state means it is the governing equation is again the Laplace equation. So, the Laplace equation is del square h by del s square plus del square h by del y square is equal to 0, where h is unknown head values. So, our unknown is h1 to h9. So, here all the boundary values are given. So, now the governing equation is Laplace equation, standard 5-point formula and diagonal 5-point formula can be applied. So, using the diagonal 5-point formula for h5, h7, h9, h3 and h1. So, this superscript indicate the iteration number. We get h5 is equal to 25, h7 is equal to 43.7.5, h9 is equal to 43.75 and h1 is equal to 6.25 and h3 is equal to 6.25. So, this is using for the first iteration. So, now using standard 5-point formula, we can get h8, h6 and h2 and h4. Here h8 we get as 53.125, h4 as 18.75, h6 as 18.75 and h2 as 9.375. So, here the superscript indicate the first iteration. So, now if you have, for example, we have already seen the Jacobi's method, Gauss-Seidel iterative formula and then successive over-relaxation. So, if you use for example Gauss-Seidel iterative formula which is given as u I j n plus 1 is equal to 1 by 4 u I minus 1 j n plus 1 the iteration plus u I plus 1 j n plus u I j minus 1 n plus 1 plus u I j plus 1 n. So, if you use this formula, now all the we can write in a tabular form like this u1 to u9 and say from one iteration to another iteration we can keep on improving the solution. So, here you can see that now the difference is almost less than 0.02 something like that. So, then depending upon the accuracy we can take a number of iterations and then we can get the solution. So, this is the solution as far as this previous problem is concerned. Here this is h1 to h9 we have obtained using the solution of Laplace equation like this. So, that is about the solution of Laplace equation. So, as you can see, Laplace equation for many problems we can use this finite difference method to solve field problem, practical problems, say in groundwater flow where homogeneous isotropic problems are there, or heat conduction problem, thermal problems. All these problems we can use the Laplace equation and that can be formulated and solved using the finite difference methods, as we have seen in the last lecture and some of the examples which we discussed here. So, now we will go to the other second equation, which is called Poisson equation. So, finite difference method formulation for Poisson equation. So, Poisson equation is very commonly used. So, there are number of applications are there. So, here compared to Laplace equation, the Poisson equation, there will be say on the right hand side also some function will be there. So, you can see that the typical Poisson equation is del square u by in 2 dimension del square u by del x square plus del square u by del y square is equal to g x y, where g is a function of x and y, or it can be also constant. So, depending upon the problem. So, this Poisson equation, number of applications are there in fields such as astronomy, heat flow, fluid dynamics, electromagnetism, etc. So, for example, we can use Poisson equation in fluid dynamics for computing the pressure field when velocity field is known, or even say for example, if you have got a groundwater flow equation, say domain groundwater flow problem like this, say for example, we know the pumping rate or recharge rate for a particular well at this location. So, now you can use the, if you know the say using finite difference method, we can solve using the finite difference method for the Poisson equation. So, let us here say for example, del square h by in 2 dimension del square h by del x square plus del square h by del y square is equal to if the pumping rate is p x y or is a constant. So, if that value is not. So, this is now the Poisson equation. So, like this we can use this Poisson equation for the solution of many problems as already discussed. So, now here we will discuss how to formulate the finite difference scheme for the Poisson equation. So, here we consider the Poisson equation del square u is equal to del square u by del x square plus del square u by del y square is equal to g x y. So, here actually this left side you can see this is the Laplace terms like del square u by del x square plus del square u by del y square, this is Laplacian term. So, this we can directly approximate and then this also can be approximated. So, finally, for n plus 1 iteration, if you consider a grid like this, so for ij this location we will be approximating with respect to all the neighboring 4 nodes. So, using these 4 nodes. So, uij n plus 1, n plus 1 iteration is equal to uij n previous iteration plus 1 by 4 ui plus 1j plus ui minus 1j plus ui j plus 1 plus ui j minus 1 minus 4 uij minus x square g ij. So, this function is there, that is will be directly coming and will be multiplying by delta x square or delta y, whatever whichever way you consider. So, this x square multiplied by g ij, that will be the addition as far as the Poisson equation compared to the Laplace equation. So, this is the formulation as far as the Poisson equation is concerned. So, we can solve many problems like by formulating as done here. So, directly we can solve different types of problem depending upon the boundary conditions and problem domain. We can make a grid like this and then put a discretization and then we can approximate the governing equation and then solve the system by applying the boundary condition. So, that is the finite difference formulation as far as the Poisson equation is concerned. So, now we will consider another equation called the Helmholtz equation. Helmholtz equation, this is also very commonly used equation. So, this is actually equations reduced wave equation used in wave mechanics, optics, etc. So, the standard form of the equation is given here. So, del square u plus f x y into u, again the multiplication of the field variable or dependent variable, that is equal to g x y. So, here this f can be a function. So, if you put f I j this. So, compared to the Laplace equation or the other equation, so you can see that the difference is that so here you can see the difference as far as the Laplace of Poisson equation is concerned. So, here the difference is this extra term. So, this extra term we can put it like this: uij n plus 1 is equal to uij plus 1 by 4 minus x square fij into ui plus 1j plus ui minus 1j plus uij plus 1 plus uij minus 1 minus 4 h square in bracket fij into uij minus h square gij. So, this is n plus 1 iteration, this is nth iteration. So, we can formulate for the Helmholtz equation as we are done for the Poisson equation. We can write, and then we can discretize the problem, and then we can solve for the given problem by first write for all the knots, unknown knots, the final difference formulation, and then we can apply the boundary condition and solve using the iterative techniques as we already discussed. So far we have seen the elliptic equation, final difference formulation. So, now we will discuss final difference formulation for parabolic equation. So, consider say the one dimensional heat conduction equation. So, here parabolic equations earlier. So far we have discussed the Laplace equation, Poisson equation and the Helmholtz equation. So, we will be discussing a variety of equation as we already seen, like earlier the elliptic, hyperbolic or parabolic equation. So, now we will discuss the parabolic equation. So, here consider the one dimensional heat conduction problem, which is called actually the diffusion equation. So, here the one dimensional heat conduction equation can be written as del u by del t is equal to del square u by del x square. So, here x is equal to, so here what we do, this is a one dimensional problem, but a time is also involved. So, here this is x direction and this is the time. So, here with respect to this del u by del t we can write del square u by del x square, this is the governing equation. So, we discretize in x direction space x equal to I is equal to 1 to 2 etc., and time is discretized t is equal to jk. So, in this direction, so k 2k 3k like that. So, we can use the standard final difference technique. So, here this del square u by del x square, which is the spatial derivative, we can write as 1 by x square into ui minus 1j minus 2 uij plus ui plus 1j. So, that is for this term del square u by del x square, and this del u by del t we can use a forward difference, for example u I j plus 1 minus uij. So, this is with respect to this and this, actually this is the time direction. So, ui j plus 1 minus uij divided by this time step delta t, that is equal to k. So, that is we can write del u by del t, and now we can combine both these to finally write the final difference formulation as far as the parabolic equation or the diffusion equation or heat conduction equation is concerned, as we have already seen here. So, here you can see, so we have already approximated for this term and then the second term, and then we have written the equation. Now, there is the governing equation can be written as 1 by k uij plus 1 minus uij is equal to 1 by x square into ui minus 1j minus 2 uij plus ui plus 1j. So, we write. So, here that is uij plus 1 is equal to, we can approximate. So, for example, if you approximate, put r is equal to k by x square, k is the delta t, h is the delta x, r is equal to k by x square in this equation. So, then we can write uij plus 1 is equal to uij plus r into ui minus 1j minus 2 uij plus ui plus 1j we can write. So, therefore, the unknown field variables values are expressed directly in terms of the known values as the values at time step is known. So, here if you see that, if you see this equation, so all these values ui minus 1j, ui ij, these all these values are from the previous time step we are putting, and then we find the current time step uij plus 1. So, therefore, this is called as explicit formulation. So, the unknown field variables are expressed directly in terms of known values. So, that is why it is called a explicit formulation and explicit final difference formulation. The unknown values at considered grid point is we get it as explicitly. So, that is why it is called a explicit method. So we can also have the implicit method. So the explicit formulation is stable only when this R, which is we already seen the R is equal to K by H square. So this R by K by R is equal to K by H square is say whenever it is here R by K H square we have already seen. So here the R by H square is between 0 to half. So then only the explicit formulation is stable. So that is already numerically it is already proven. So now if the Gavani equation is replaced now, so instead of the explicit method we can have the implicit method. So what we do in implicit method, so here this the space derivative del square U by del x square, we take it average of its approximation current and the next time step. So the here j and j plus 1, j is the previous time step and j plus 1 the current time step. So we will take the average del square U by del x square will be the average of this ui minus 1j minus 2 uij plus ui plus 1j plus this is the next time step ui minus 1j plus j plus 1 minus 2i j plus 1 plus 2 ui plus 1 j plus 1. So that is with respect to this is these values, and with respect to this we take the spatial derivatives concerned, we take the average del square u by del x square. So then the Gavani equation becomes so like this. So here 1 by k is equal to ui I j plus 1 minus uij is equal to 1 by 2x square into ui minus 1j minus 2 uij plus ui plus 1j plus ui minus 1j plus 1 minus 2 ui j plus 1 plus ui plus 1 j plus 1. So we write like this, and now as we already put here r is equal to k by x square. So we can approximate, we can put simplify this equation as minus r into ui I minus 1 j plus 1 plus 2 into 2r into ui j plus 1 minus r ui plus 1 j plus 1 is equal to r u I minus 1 j plus 2 minus 2r ui I j plus r ui plus 1 j. So like this. So here you can see there are 3 unknown terms and 3 known terms in this equation. So j plus 1 is already unknowns and jth terms are all known values. Previous time step j plus 1 is the current time step. So previous time step all values are known, and current time step 3 values are unknown. So this, when we write like this is called implicit scheme. So generally it is called Crank-Nicolson formula. So here we need to write for each location like this using this equation, and then we need to solve it together. So we do not directly get a solution, it is solution is implicit. So that is why it is called implicit scheme, and this equation is generally called Crank-Nicolson formula. So here advantage the solution converges for all finite values of r. So larger values also can be considered. For example, if your time step is larger, so then larger values of r will come. So still it will be stable, since we are considering all the nodal equations together and then apply the boundary condition and solve it together. So the implicitly only we get the solution. So that is why it is called implicit method, and it is more stable. So that is the difference between implicit and explicit method. So if there are n nodal points in each row, this formulation gives n simultaneous equation for the n unknowns in terms of the boundary values. So that is about the implicit and explicit formulation, implicit finite difference method and explicit finite difference method, its difference and then how we formulate. Now before closing this lecture, we will see one example. Solve del u by del t is equal to del square u by del x square subject to u x 0 is equal to 0, u 0 t is equal to 0, u 1 t is equal to t. So this is the domain. So here this u at x 0, this all values are 0, u x 0, this is also 0, and here the one value is known. So choose k is equal to 1 by 8 and delta x equal to 1 by 2 or h is equal to 1 by 2. We will get r is equal to k by x square is equal to 1 by 2. So now you can use the previous equation. So here this equation we can directly utilize to solve, right, for all the unknowns. So here actually in this problem, if we use this ks or delta t is 1 by 8 and delta x is 1 by half, actually there is only one unknown. So this is the unknown. So using Crank-Nicolson formulation, from this we can write ui minus 1 j plus 1 plus 6 ui j plus 1 minus ui plus 1 j plus 1 is equal to ui minus 1 j plus 2 ui j plus ui plus 1 j. So, here for u at t is equal to 1 by 8 and x equal to half, at point P only one unknown will be there. So, here we can write the equation like a 0 plus 6 u1 minus 1 by 8 by using this boundary condition, and we can directly get u1 is equal to 0.0208. Actually, this is only one unknown, so it is a very simple problem. Now, the same problem we will solve it using here k is equal to 1 by 8 or delta t is equal to 1 by 8 and delta x equal to 1 by 4, h is equal to 1 by 4. Actually, only 1 by 8 time step, but we are having delta x is now only it is 1 by 4. So, we have got more unknowns. So, here these boundary values are known, this is known, this is 0, this is 0, and here this is u is equal to 1 by 8, this value is known. So, here apply the Crank-Nicolson formula. So, here we are having 3 unknowns u1, u2 and u3. So, we can write for all the unknown values, we can write the 3 equations by using the Crank-Nicolson formula as written here. So, here we will be finding the unknowns at P, Q and R. So, applying the equation at P, we can write 0 plus 3 u1 minus u2 is equal to 0, that is 3 u1 is equal to u2, and applying the equation at Q, I mean this location, we get minus u1 plus 3 u2 minus u3 is equal to 0, and then applying equation at R, this location. So, we get minus u2 plus 3 u3 minus 1 by 8 is equal to 0. So, these 3 equations we are having this boundary condition, and now we can put the boundary condition and solve for the unknowns. So, that is the way we can solve it. So, here now in this lecture module number 4, lecture number 4, we have discussed the how to use the final difference scheme for Neumann boundary condition or derivative boundary condition, and also we have solved a problem with respect to Laplace equation, and then also we have formulated for the Poisson equation and Helmholtz equation. Then further we discussed the final difference formulation wherever the heat conduction problem or the diffusion equation del u by del t square del square u by del x square in 1D, and we have already formulated it using the explicit scheme and implicit scheme. We have differentiated between explicit and implicit scheme. So, as I mentioned, implicit scheme is more stable and we can use larger time steps, but in explicit scheme the time step should be very small to get a stable solution. So, that is about the lecture number 3, lecture number 4, module number 4. So, now before closing we will discuss one assignment number 4 for module number 4. Okay, so here we discussed the assignment number 4 for lecture number 4, module 4. So, here we are having 2 problems. So, one is the for the Laplace equation, and the second one is the Crank-Nicolson scheme. A homogeneous first question number 1, a homogeneous isotropic aquifer has the boundary condition as shown in the figure. Assume steady state condition. The governing equation can be given as del square h by del x square plus del square h by del y square. So, this is a very simple problem as we have already seen earlier. So, these are the unknown h1 to so here the 9 unknowns are there. So, we can directly solve it by considering all these boundary conditions. So, that is straightforward. So, now the second problem is derive the Crank-Nicolson scheme formulation for the groundwater flow equation 2-dimensional homogeneous isotropic confined aquifer which does not have any source and sink. So, here the governing equation del square h by del x square plus del square h by del y square is equal to s by t del h by del t. So, this is the problem. So, here we have already seen in lecture number 4, module number 4 for one-dimensional parabolic equation or heat conduction problem del square u by del x square is equal to del u by del t. So, very similar way now you are asked to extend for 2 dimensions. So, that is very straightforward. You can do it as an implicit formulation. So, here this is the governing equation. So, this also is given as assignment. So, with this we close the lecture number 4, module number 4. So, further we will be discussing more on the final difference scheme for other equations and then also other schemes. Thank you very much.